So we're now looking at the second session, and I'm going to talk about heterogeneity in meta-analysis. The time for this session and the corresponding practical is relatively short, unfortunately, because we want to get on fairly quickly to talk about the sources of bias in meta-analysis and how we're going to address those, which is Goethe's talk. So I hope you've got started with the practical. Some people will probably have finished, and some people are probably still at the beginning, and that's inevitable with a course like this, where we've got people from a wide range of backgrounds with different levels of familiarity with the software. But we're happy to support you through the day, at whatever stage you're at with the practicals. So we're going to introduce random effects models, and as a way to model and take account of heterogeneity, so that's greater extent of differences in treatment effects between studies than the fixed effects model would allow for or expect. And we'll talk about how to detect it, and we'll talk about some statistical methods for actually trying to understand and explain sources of heterogeneity. And then in the practical, we'll see how we can very nicely and easily extend some of the analysis we did this morning in R to perform these additional analyses to investigate and understand heterogeneity. So key to all this is to extend our fixed effects model from this morning to a random effects model, and once again we have that. Is this not working? Because it's not turned on. We have that theta hat k is the estimated effect from the kth study, but now instead of having that directly related to the overall effect, we're saying that this effect is in fact distributed around theta k, so around the true value for studies, say, of that design in that population. And then this, in turn, is going to be normally distributed about the overall mean. So as I say, theta hat k is the effect from study. That should be k. Theta k is the true mean for study k, and it's the standard error. And these means theta k vary randomly about the overall mean. And this then is that variance of that distribution, and that's the heterogeneity variance. So essentially, we're extending our regression model from this morning by allowing for an additional source of variance. So here's the overall effect, here's the effect from study K, and the variance of this about this depends on the between-study heterogeneity and then the within-study variability. So if you want a graphical way of looking at that, you can think about it as follows. So the black line is the line of no effect, and the grey line, or a blue line on my screen here, is the average effect, so that's theta. So then for each study, we're going to see an effect that's drawn from a distribution about theta with variance tau squared, and that's what we see in this curve here. That's a normal distribution with variance tau squared about our overall effect theta. So our study effects then are theta k's, so these are not the estimates, these are the true value for study 1, 2, 3, 4, 5. They're going to be drawn from this distribution. And then we're going to do a study 1, and then because we do study 1, we get an estimate of the true effect of studies of this type, and that itself has variability because we've only included a finite sample in study 1, and so that then gives us our theta hat k. So our theta hat 1, our estimate from study 1, is normally distributed about theta 1, which is in itself normally distributed about theta. So the variance of theta hat 1 around theta 1 is sigma squared 1, and the variance of the diamond here, theta 1 about the overall theta, is tau squared. And so we go on then like that. And then these are the actual estimates of theta that we get from the first study, the second study, the third study, the fourth study, and so on. And there are their confidence intervals. Okay? So as we'd expect, the confidence intervals for each of these studies includes the true values, just in some cases, but they don't include the overall value, all of them, because of this additional source of heterogeneity. So a straightforward fixed effects analysis in this setting is inappropriate because it ignores that heterogeneity. We can avoid that by extending to the random effects model. Okay. So once again, we're going to do a weighted estimate. Our overall estimate is a weighted sum of the estimates from each of the studies. But whereas in the fixed effects model, the weight was just 1 over the estimated variance from the study, so the weight for the kth study, 1 over the variance from the kth study, the weights in the random effects model have the addition of the estimate of the between study heterogeneity tau squared. So clearly, as we get large heterogeneity, tau gets larger and larger and larger and dominates this, and then all studies tend to get similar weights regardless of their value of their specific value of sigma squared. And in particular, what we see with random effects analyses is it generally gives more weight to the smaller studies because we have this term added to all the weights, and so that increases the weight for the smaller studies proportionately greater than it does for the large studies. And that's an important observation for talking about bias later. Okay, so here's the forest plot from overall survival for the first talk, and now what we've added here is the random effects model point estimate of theta and its confidence interval and the corresponding weights. If you look at these, you'll see exactly as I said, smaller studies have got proportionately greater weight in the random effects analysis. So if we think about the random effects model in a little bit more detail, we see that we've got the estimates from the studies varying about the study-specific mean, which then varies about the global mean. So a priori, before we collect the data, the true values for each study are assumed to be exchangeable. They vary randomly about the overall mean, exactly as I saw in that distribution that I showed you a couple of slides back. So what we're basically saying at one level is that different studies are showing slightly different effects. There's a sort of study-treatment interaction, and the way we're handling that is by treating that as a random sample from a population of treatment effects. So Stephen Sen has written quite well on this, and it's very worthwhile to read what he's got to say in these papers. Confidence intervals for the random effects model, if you follow through the implications of what we had on the previous slide, are always going to be at least as wide as those for the fixed effects model, and that's what we want, because we want to acknowledge that uncertainty in our confidence intervals. We don't want to brush it under the carpet, as we would do if we had heterogeneity tau squared is greater than 0, and we just fitted a fixed effects model. If you think about it from a Bayesian perspective, you can calculate the posterior predictive distribution, and Higgins and colleagues in 2009 showed how you could use this to calculate a range of effects for possible future studies. And of course, the fixed effects model is a special case of the random effects model when there's no heterogeneity. Okay, so the causes of heterogeneity, as anybody who's looked at any data will know, they could be because different types of patients are going into the studies, and the way that's dealt with may not be reflected in the outcome measurement scale properly. Heterogeneity from other sources, different designs, possible heterogeneity in the way studies come to be reported, and we'll think more about that later. And all of this then is brought together and modeled through the statistical heterogeneity. So there always is heterogeneity. The practical question is whether it's important for the clinical inferences we wish to draw. In other words, what is the size or magnitude of tau squared relative to the overall estimate theta. Okay, so the way we can think about this is by using our random effects model, by performing subgroup analyses to try and understand the sources of the heterogeneity, and then by going further and doing meta-regression and trying to understand if heterogeneity relates systematically to, say, some characteristic of the study, the dosing, for example, and then we can statistically model that. So the random effects model adjusts for heterogeneity, but it doesn't explain it. The subgroup analysis actually tries to explain how heterogeneity might be arising because we've got, when we look more closely, our studies fall into different groups, for example, whether or not they used randomization or some other measure of quality, and those that maybe did use randomization give systematically different results from those that didn't. Another possible example is high versus low risk patients. And then meta-regression extends this, so we can do subgroup analysis for continuous variables. And we've got an example of this that we'll look at later. So we can look at an example in patients with arterial fibrillation. And we've got amiodarone compared with all these groups on the right-hand side, placebo, and so on and so forth. And the primary outcome is conversion to a more normal heart rhythm within 4 weeks. And so this is just summarized as 1-0, yes or no in this presentation. So we read the data in R, and you should be becoming more familiar with this code after the practical this morning. And then we can do a forest plot. And we do indeed see that there's quite a lot of heterogeneity in this slide. Okay? We can look at the results of the meta-analysis summary. And we see that we've got 21 studies here. And the fixed and random effects estimates are a little bit different. The estimate of tau squared is 0.06, and the heterogeneity statistic in this case is measured by Q, and we'll define Q in a minute or two, and that shows that there's much more heterogeneity amongst the studies that we would expect by chance, and that would lead us to preferring the random effects model to the fixed effects model, and also and very importantly, trying to understand the sources of this heterogeneity. So we should always plan our principal subgroup analyses beforehand to guard against the possibility of just dredging the data. And here a predefined subgroups analysis was the duration of the current arterial fibrillation episode, and so it's less than 48 hours versus more than 48 hours, and there are other possible groups for these data listed out on this slide. Okay, so we're going to look at the top one, and down below at the bottom, you can see that we can update the current meta-analysis. We could do it all again from the beginning, but it's often much more convenient to update what we've got. And we're going to do subgroup analysis, and the argument to do that is bivar, and here we give the variable that defines the subgroups. And here we have allowed for a different heterogeneity variance, tau, in the subgroups, and here we've insisted that it's common. We'll discuss a little bit more about that in the practical. So let's talk a little bit before we come to the results of that about the notation for subgroup analysis and the measure of heterogeneity. So we've got P subgroups of studies, and within subgroups we've got KS studies. K is 1 to KS. Okay, so within subgroup S there are KS studies. K, the total number of studies, is the sum of KS from S going to 1 to P over all the subgroups. So we can calculate a weighted mean in each subgroup using a fixed or preferably a random effects model. And then if we sum those all together, we come back to our random effects estimate. So here's the forest plot of the arterial fibrillation example. And so you can see that when we split on the duration of the arterial fibrillation episode, less than or greater than 48 hours, there's something quite different going on in these patients who have more serious disease. Okay? And we've already talked about Q a couple of slides back, but now we'll define it. So from each meta-analysis, we've got an estimate of the effect and an estimate of the variance. And so therefore, we can use the sampling distribution of the squared differences about the mean and compare that with a chi-squared distribution and do a statistical test to assess the amount of heterogeneity, whether it's more than we'd expect by chance. So we can do this overall, we can do this within groups, and we can do this between groups. Okay? So we can look at the overall heterogeneity, and we can say what proportion of that is due to between group variability, and what proportion of that is due to variability within the group. So in the arterial fibrillation example, what we'd hope is that there's quite a big difference between the two groups, but then within the two groups, depending on whether the arterial fibrillation has been for less than 48 hours or more than 48 hours, there's not so much heterogeneity left over. Okay? And as I said a minute ago, then the total heterogeneity is summarized like this. Okay? So clearly, there are links here to regression. So this is very nice, and we can calculate these statistics very easily in R, and we can say that, so for the shorter duration, okay, the Q statistic was 30.6. So there's still, let's have a look here. So between groups, there's significant variability. Within groups, there's still a little bit of variability because there's quite a lot of variability amongst these studies of shorter duration, but amongst the longer studies, then basically they're more or less giving, amongst the studies carried out on those with longer duration, they're more or less giving the same answer. There's not much, the estimate of between study heterogeneity in that group is 0. Okay? So we have explained not all, but a substantial amount of the heterogeneity by doing this analysis. And so we'd be much happier then with reporting that than just reporting the overall summary without looking into the subgroups. Okay. And so we can also see here, so that's the statistics we've had already. And these are the two subgroups. These are the estimates in the subgroups. And the confidence interval. So it's just escaped me now. So this at the top of the slide is these are fixed effects estimates. these ones, what's the difference between this group here and this group here? Can't remember. Pardon? This one is random effects. Hence, the confidence interval is wider. Yeah, okay. So this one, because we've got random effects analysis here, but this estimate is the same as this estimate because the tau squared here is 0. And finally, we can repeat the analysis, but now saying that tau squared is common between the two groups, and then you get slightly different results. So if you want to, when we do meta-regression, so we extend the subgroups analysis to meta-regression, we generally say that tau squared is common between the two groups. Whether you want to do that in individual analysis depends a little bit on the context you're looking at. Okay, so we'll talk briefly about meta-regression. So here's a fixed effects meta-regression. So we're basically saying that here's the overall estimate, and then the effect we get for any study K depends on the covariate xk mediated through this regression coefficient beta. Random effects is the same, but now we've added the heterogeneity term here, as usual, with variance tau squared. Okay, so we can do a subgroup analysis, which we've just done more formally using meta-regression, just defining xk to be 1 if the duration is greater than 48 hours, and 0 if it's less than 48 hours. So this is how we do it in R. Okay, so it's very straightforward, and we'll look at some results in the practical as well. We can do a bubble plot, which is quite a nice way to visualize this, especially if we've got a variable here which is continuous. So here we've just got two categories, or a variable that's ordinal. And so what we see here are the study effects, and the size of the circle is proportional to the information contained in those studies. So in other words, 1 over the variance. And then we can see that you can see quite clearly that the point estimates are different for these two groups of patients. And you can see that while there's relatively little heterogeneity in the group of studies among patients who had duration greater than 48 hours, there's relatively more in the duration less than 48 hours, which is consistent with the numerical summaries we looked at a couple of slides ago. Okay, so here's another example, and we're going to use this to look at a meta-regression. So it's a vaccination example. Here's the forest plot. So we produce that in exactly the same way as before. And we now see that there's quite a lot of heterogeneity, and the random effects estimate is quite different to the fixed effects estimate. Okay. So it's vaccine for the prevention of tuberculosis, 13 prospective trials, and the covariate we're going to look at is the distance, the geographical latitude, distance from the equator, okay, and to see if this affects how the vaccine performs, and that's a proxy for all sorts of factors that could influence the outcome of these studies. So here's the code to perform the analysis at the bottom. To produce a forest plot, and we're going to sort on the latitude. Okay. So you can see then our forest plot now is sorted on the latitude, with latitude increasing here, and indeed we do see a bit of a trend with latitude. Yeah. We could also have inspected this with one of the bubble plots that I showed you earlier. So now we're going to do the random effects meta-regression, and the command is very, very simple, just meta-reg and you've got the object you created before, M4, and the covariate here, and it gives you the intercept, and it gives you the effective latitude. And we see straight away that latitude does indeed explain a lot of the heterogeneity here. Okay? Clearly, if you're going to interpret this intercept, you need to think about the value of latitude. So if this value here is the value where latitude is 0, and you need to think about if that's where you want to report the effect. So you need to be a little bit more careful in the interpretation. There's our bubble plot. Okay. And as we can look at in the practical, you can see whether the variability after you've adjusted for the covariate is more or less than you'd expect. So you can see what the extent of the residual heterogeneity is. So there's a number of caveats with meta-regression and subgroup analyses. You need to look at the data, so that's not unique to this form of analysis. That applies to all kinds of statistical analysis. There's almost always unexplained heterogeneity after you've done a meta-regression, and therefore that unexplained heterogeneity should be carried forward into the inference for your overall treatment effects. In other words, you should do a random effects analysis with meta-regression, not a fixed effects analysis. There's a risk of spurious findings, so you need to have really at least 5 studies in each of the groups if you're going to do subgroup analysis. You need to limit the number of covariates you're using, preferably pre-specifying them. And your covariates need to be operating at the study level, really. Otherwise, we can get this, we're at risk of misinterpreting what's going on due to the ecological fallacy, where at the aggregated level, we can see different relationships from those that are actually going on at the within-patient level. Obviously, if you've got within-patient, individual patient data, you can look into that. Okay. So I've already touched on the use of study-level variables. You shouldn't really use baseline risk, and ideally, each study would have adjusted for baseline risk in the treatment effect it had reported. If you've got individual patient data, then meta-regression is very nice to do because you can take into account the patient-specific variables as well as the study-level variables. Okay. So we don't want to do a fixed effects analysis if we're at all concerned about heterogeneity. Instead, we want to understand the sources of that heterogeneity and really adjust our analyses and our inferences appropriately. So because we know the mean and the variance from each of the studies in our meta-analysis, we can look at a heterogeneity statistic Q. We can see if there's more heterogeneity than we'd expect under the fixed effects model, and then we can pinpoint the causes of that heterogeneity by decomposing Q and understanding the how heterogeneity is spread between subgroups and within subgroups. As I've already said, if heterogeneity is present, we should use the random effects model instead of the fixed effects model. But of course, if studies are systematically different, we should probably be reporting separate effects for the different types of studies rather than trying to combine them into one overall effect. And you need to think carefully about the context when you go into that. Okay? One important source of heterogeneity is going to be not just sort of due to different clinical groups, but actually due to systematic biases, and that's going to be the subject of Geerte's presentation in a minute. So that's the end of this presentation on introducing heterogeneity and how to take account of it when you're doing meta-analysis in R. Here are some of the references referred to in the talk. So Should we, well, I'm happy to take any questions. I've been happy to take any questions all along, but you've all sat very quietly. I think we've got our mic somewhere around. Has anyone got any questions at this point? Yep. And then just while you're getting the mic, should we try the heterogeneity practical now, do you think? Or should we go straight to the bias presentation? Yeah, okay. So what we'll probably do, if it's okay with you, is that we'll follow straight on with the bias presentation, and then we've got a good block of time to work on the practical materials. And the materials... For the practicals for the two presentations lead very closely to each other. Sorry, so you've got a question?
Yes. I don't know if I understood well, but I should predefine if I will have a heterogeneity adjustment or not. Is that correct?
Ideally, yes. So if you're involved in a team that's doing a systematic review, then as a statistician, you should say to them, have a think about whether there are likely to be systematic differences between subgroups of studies and what's likely to cause that, and then take some notes about that and try and highlight or home in on a group, say, of 2 to 3 covariates you might like to use to explore possible heterogeneity, pre-specify that, and then set that to one side, get on with the systematic review, getting the data, reading the papers, and so on, and then when you get to the formal quantitative meta-analysis, have a look and see whether those covariates actually explain much of the heterogeneity. Yeah.
So I shouldn't base my decision on the outputs that I get from...
Well, if you do, you need to acknowledge in the reporting that these subgroups turned up in your data unexpectedly. And therefore, the analysis is more for the purpose of generating hypotheses for the future in terms of those subgroups than definitively saying, these are our pre-specified subgroups, here's our test, we conclude that there is heterogeneity between these subgroups. So it's the usual balance with statistical modeling. It's best to pre-specify. If when you've got the data, they are really telling you very strongly that something else has happened, then you'd be daft to ignore that.
So the last one is, for me, it's a little bit counterintuitive, giving more weight to small studies.
Yes, and I think that's a good point. And so there's been a lot of discussion in the literature. I think there's been a whole issue of the journal Statistical Methods in Medical Research some years ago devoted to whether one should prefer fixed or random effects meta-analysis. And different people put more weight on relative properties of the different methods and then come to different conclusions. So my take is that if the point estimates are similar for fixed and random effects analyses, then we're actually in the situation of slide 5 at the top there, when the effects are actually coming from some true average distribution, okay? And then I would do a random effects analysis because I would want to reflect that heterogeneity in my standard errors and my confidence intervals. In the examples, some of the later examples we looked at and some of the ones that Goethe will look at and you'll look at in the practical, the fixed and random effects estimates are very different, and then we need to understand the sources of that heterogeneity, because following on from what you say, if the fixed and random effects are different, that often says that the smaller studies are doing something systematically different to the larger studies, and we should not just blindly go ahead with reporting a random effects meta-analysis because there's heterogeneity in that setting. We should try and explore and understand the sources of that heterogeneity.